next speaker is Spenta Wadia. He will tell us about black hole dynamics in the SYK model, holographic to two-dimensional gravity. Please, 45 minutes.
Okay, thank you very much for the invitation. And I wish I was in Moscow in person. Hopefully next year or year after I can come there.
Yes, yes.
It has been my dream to visit Russia and Moscow. So thank you for the invitation to give this talk. And I'll be talking about black hole dynamics in the SYK model, holographic to two-dimensional gravity. It's earlier work based on this paper with Avinash Dhar, Advait Gaikwad, Lata Joshi, Gautam Mandal, and myself. And also towards the end, I'll mention some work that we are doing, continuing this project with A. Gaikwad, Kaushal, Gautam Mandal, and myself. So Advait Gaikwad is a student on this project with also Anurag Kaushal. I just wanted to mention that. Okay, so the main motivation for doing this work is the following, that the black hole information loss is usually associated with black hole evaporation, which everybody knows. So I'm not going to explain all that. So many speakers in this conference have already done that. But there's also a form of information loss when a black hole is formed out of a pure state. Because if you start with a pure state over here and it forms a black hole, and the black hole is described by a certain mixed state density matrix. So it's some sort of a reverse thing that we would like to discuss explicitly. And in the ADS CFT correspondence, in the CFT or in the field theory on the boundary, this really corresponds to a pure state which is subjected to a quantum quench, and then it thermalizes and is described again by a certain density matrix. So in order to do this in a precise way, we are fortunate that there is a very good simple model called the SYK model, in which we can do explicit calculations. So I'll describe the SYK model very briefly, because it's by now a very famous subject. Is the Sachdev E. Kitaev model. It's a soluble model of two-dimensional gravity. And after all the dust settles and complicated calculations are done, the low energy effective action is this Schwarzschian over here. And this Schwarzschian is not very difficult to arrive at. What is difficult to calculate is this number, which depends upon the ultraviolet physics. But that's not important for us. The second important property of the SYK model is that it actually exhibits chaos and operator scrambling, as we heard from Julian's talk earlier. And this is the precise result for the Lyapunov exponent that is saturated to be 2 pi times the temperature of. Third important property of this model is that it has microstates, and low energy pure states are easy to construct from. A large part of this talk has to do with microstates and their low energy projection. And the last important thing why all this is very useful is that it helps us to understand black hole physics in the dual space, which is the ADS spacetime. And one important point I want to make is that this field theory is, this theory on the boundary here is not a conformal field theory. And in fact, I really don't know any conformal field theory, any conformal quantum mechanics actually, which has a holographic dual, which describes ADS2 spacetime and black holes and stuff like that. Okay, now let me continue describing the SYK model and also the addition to the SYK model by Kurkulu and Maldasaina. So I think again, Julian has very nicely described in very lovely pictures the SYK model. So I will just also repeat that without very lovely pictures. The quantum mechanics of n, it's just a quantum mechanics of n real fermions with an all-to-all random interaction. And these are the anti-commutation relations. This is the Hamiltonian of the SYK model. I will restrict to interactions which only involve 4 fermions. And this is the Gaussian distribution of this random coupling over here. Now, Kurkulu and Maldacena, in what I think is a rather fundamental paper, explored the problem of whether you can see the microstates in the long wavelength regime, and introduced, in addition to the SYK model, a Hamiltonian, which is essentially made out of a new Hamiltonian, which is actually a relevant operator in the infrared. In the infrared, as you know, the anomalous dimension of the fermion is 1/4. So this is really operator of dimension half, and hence it's relevant. So they added this anomalous, additional operator. And however, this operator has certain fixed numbers associated with it. And I'll come to what those fixed numbers are. At the moment, this is just some string of numbers plus or minus k in each of these boxes over here. And we'll see later that these numbers, these set of 2 to the power of n upon 2 numbers actually spans the Hilbert space of the full SYK model, and is essentially are the microstates. So before I go further, I'd like to actually summarize very briefly the results, so that in case you fall asleep during my talk, you will at least know what we have done. So the results are the following. So the SYK model provides a simplest holographic model that enables a computation, a real calculation of the process of black hole formation in the bulk. I mean, it is very difficult to imagine being able to do this type of calculation in more higher dimensional, more complicated systems, but here we can do it. And we compute the evolution of pure states through 2 quantum quenches. I will explain in detail later on. The first quench of sufficient strength basically was introduced by Kurkulu and Maldacena, and it abstracts. It's like putting a certain refrigerator on the boundary of the ADS space that extracts the energy out, and the horizon and the resulting geometry after this deformation is put in with a certain strength, the horizon disappears. So you have a space-time without a horizon. But what we did basically is understood this formalism and made it more rigorous, and we introduced a second quench a large time later, which pumps energy into the system. We put on a certain heater, and that of course leads to the formation of a black hole, and we can calculate the evolution of the functions which describe this black hole, and from there we can exactly calculate the temperature of the new evanescent black hole, the final state, and it turns out to be of this particular form. It's of a certain scaling law, which reminds you of the Chopwick scaling laws in higher dimensional black hole physics. Okay, so this is what we have done. Now let me start with the microstates of the SYK model. So they are very simple to enumerate, because these commutation relations of the SYK model are nothing but the defining relations of Dirac gamma matrices of the group SON, because we have n Majorana fermions. And I just wrote down a very simple representation. Everything can be really explicitly done here, and that's the strength of this simple model, that in the kth space over here, gamma 2k minus 1, you have this sigma 1, and here you have sigma 2. And if you multiply these, you essentially find the sigma 3. And it's in terms of the eigenvalues of this operator, this last operator, which was introduced by, recognized as important by Kurkulu and Maldacena, that you essentially have an operator that commutes for all k with itself and has eigenvalues plus or minus 1 because its square is 1. And so you have a very beautiful and simple characterization of the Hilbert space, which is spanned by this orthonormal states, which I have just described for you. Okay, so these are the microstates. Now, it so turns out, if you compute the energy of these microstates, that these are very high energy states. And so they cannot be, in order to probe them by simple methods, it is not possible. So let us try to understand a low energy projection of this microstate over here by the standard method of, by multiplying it, evolving it in Euclidean time, L, which is precisely the inverse temperature divided by 2 over here. Okay, and we assume throughout this talk that L is very, very large because we are interested in low energy physics of this problem. So this is an overcomplete set of states. All right, that's point number 1. So the other thing which is very important in this problem is the discovery of what is called a flip group. I mean, all this is known in some sense in group theory, but Kurkulu and Maldacena actually use this in a very beautiful way, as I will explain to you. And let's describe what the flip group is. The flip group essentially is a subgroup of SON. And all it does is basically it flips the sign of the even fermions, this one over here, but leaves the odd fermions intact. So basically it is its generator, this group element is basically given by psi of 2k minus 1. It's not important what the explicit form is. So you have these operators which are even and odd. Of the whole theory, you can classify the operators as being even and odd under the flip group. And in particular, the spin operator, which I talked about before, is odd. And hence the entire Hilbert space, which we described a little while ago, is basically an orbit of the flip group. So if you start with just these plus, 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 all of them, then by successive application of the flip group, you can arrive at any state in the Hilbert space. So this is a important property of the flip group. Okay, now how do you use this? So this is the topic of thermal properties of pure states. These pure states I have called BSL, where L is very large. Okay, and here is a definition that if you take expectation value of some operator and you sum over these eigenvalues, these microstates, then of course this is by definition the trace of the operator times exponential of minus 2L H0, which goes in the definition of BSL, of course. Now there is a very important little theorem one can prove, a lemma, that if O hat, this operator, is flip invariant, then this entire thermal expectation value is evaluated without summing over SK for obvious reasons. So if you take any SK, any collection of the microstates and evaluate the expectation value of this operator, then you will just get the thermal average. So this was a very important realization that you can construct explicit microstate, take its low energy projection and lots of operators which thermalize with respect to this particular definition of the microstates. Okay, and for example, I'll just give you 2 examples without much discussion. That look at the partition function. The partition function is nothing but the expectation value of this, and it is, these are pure states for any particular realization of S, and it gives you nothing but the trace of exponential of minus 2L H0. And again, you can also calculate, for example, the 2-point function when these 2 indices are identical. I'm not summing over them, and this is the answer which you get, which is sort of the very interesting answer for the thermal Green's function in Euclidean space. Okay, so these are quite well-known results. Now, let's get into a little bit more of dynamics, then that we would like to understand the time evolution of these BSL states. Okay, and this parameter epsilon of t is what I call the quench parameter it is piecewise constant. Okay, so for some interval of time it has a certain value, for some other interval of time it has some other value. Okay, so this is the Hamiltonian system we want to work with, and we want to study the effect of time evolution by two Hamiltonians. One is the full Hamiltonian, which is the SYK Hamiltonian, plus the relevant operator. That's a full Hamiltonian. And secondly is a wave function which will just sail along by the standard SYK Hamiltonian. So I would like to compute the overlap of this two wave functions. And this is a central object of our mathematical discussion in this problem. And we like to compute this overlap. And this, if you open it out, this overlap essentially has this very simple form, which is illustrated in this diagram over here. And it says basically that you start with a BS state over here and evolve it in Euclidean time for distance L. And then you make a right turn and go for a very, very long time in real time. And then you come back using this Hamiltonian back here to compare yourself, to compare with the BSL state that is constructed again from here by the action of e to the minus LH naught. So you go this way, you evolve again in this with this same Hamiltonian, and you reach here. And this is the sort of a pictorial way of talking about this average. Okay, so this contour is in the complex time plane. There are very fancy ways of talking about all this. And we did a rather explicit calculation to somehow compute this ASLT, not only for low energies, but for arbitrary energies and only in the large n limit. I will not write down that formula, which is in our paper, because it's not necessary for me. And I'll just quote the result over here, that the result at large n and low energies for this overlap is simply given by the path integral of over the reparameterization mode over this action. And this action is essentially the original SYK low energy action, which is Schwarzschian. But there is an additional term that comes from this relevant operator, which I had introduced. And in this problem, we are looking at delta is equal to 1/4, because you are working with 4 fermions. And so this exponent here is half. And this contour is there. So this contour is very important actually in what follows. So these are details, but these details I will not be able to go in over here. So now for the moment, let's forget about the SYK model and review a little bit about the bulk problem, the bulk dual gravity problem. Now in 2 dimensions, there are 2 natural theories of gravity which are dual to the low energy physics of the SYK model. The first one is the one we had considered some time ago. It's a Polyakov gravity. Polyakov gravity with a cosmological constant, and these are the standard boundary terms for this action. And this action actually arises from the quantizing the co-adjoint orbit of diff 1 upon SL2. And 1 here means basically either it can be R1 or S1. So if you look at this method of co-adjoint orbits, which was developed very beautifully by Alexeyev and Satashvili, then you find essentially that in the infrared, the co-adjoint orbit of the SYK model is described essentially by this gravity action, and you get this additional dimension for free. That was our whole motivation to look at it this way, that how do you get from a 0-dimensional theory moving in time to essentially a 1 + 1 dimensional theory of gravity. And this is actually a very beautiful example of this type of thing. Okay, but it's quite complicated to work with. That's why it's not very fashionable. The other theory of gravity, which everybody works with, is obtained by a S-wave reduction of a near extremal charged black hole in 4 dimensions in this particular way. This is the dimensional reduction, and this is a action which everybody works with these days, so I'm not going to belabor it. This is the dilaton field, and this is the curvature plus twice the cosmological constant. So essentially these are negative curvature spaces, and about which a lot of people have worked quite a bit. And this is the expectation value of the dilaton is supposed to be large in these theories. So this is the Joukov-Teitelbaum gravity. But what is nice is actually that in both theories, there are no propagating degrees of freedom. Okay, both theories, clearly. And the only physical degrees of freedom in both theories, Polyakov gravity and Joukov-Teitelbaum, are large diffeomorphisms, which I've just indicated over here. So if you call the two-dimensional space-time tau and z, then this is the diffeomorphism. And these diffeomorphisms are physical and near the boundary. Large diffeomorphisms are physical and near the boundary, that is near in Poincare coordinates. I'm talking about this. The diffeomorphism near the boundary turn out to be precisely given by this function. This is a very important point actually, that this is equal to this, and near the boundary z equal to 0, z itself is proportional to z times the time derivative of f prime. This is a very fundamental point which I will explain. We play a very important role in our work. Okay, now with all this action and all those things, these are the geometries which come by solving the equations of motion. And just some pictures over here. So this is the Euclidean geometry. This is the Poincare disk, and then essentially it's parametrized by this space of maps which belong to diff S1 mod SL2R. This is very well known, so I'm not going to explain all this. But this is the Lorentzian model of ADS2, and here, if you make this, you know, in this subject, there are lots and lots of coordinate systems that keep on changing hands. So I'm not going to go into all those details, but all I want to say is that this diagram over here essentially describes ADS2. I should have put these two lines, and this is the Poincare wedge over here, this one, and this is the horizon, and this is the trajectory of the particle. This particle, you know, f of t essentially describes some particle dynamics controlled by the Schwarzian action, and the solutions are such in this particular example, so that the time derivative, you see the time derivative here and the time derivative here is 0. And because the time derivative is 0, the information which somebody over here will send out will not be able to reach the observer over here, and therefore a horizon forms. So this is a very important little point. It's a very beautiful point that formation of horizon in this two-dimensional geometry is related to this dynamics of this particle f of t and whether it hits a 0 or not. So we'll see that this is very useful actually, and I have actually explained this over here in this box. I just said this actually, that in Poincare coordinates near z equal to 0, this is a large diffeomorphism, and near the boundary it has this form, and if f prime of t equal to 0, then this guy, this z of the deformed z of f actually hits a 0. If f prime is not 0, it doesn't hit a 0, and the observer cannot receive signals from the entire Poincare patch, and there's a horizon. So this is a very elementary observation, essentially also makes doing things rather very simple, and you can solve the equations of motion of these Euclidean theory and the Lorentzian theory, and these are the formulas, the very famous formulas actually for f of t, f of tau, and f of t. Okay, now comes the difficult part. So we essentially, in our problem, if you remember, I'm sorry for scrolling this much, that over here, over here, there sits this state BSL actually. So it's a sort of a marked point in this problem, and the question is, what is the geometry actually in the presence of this state? So I just want to spend a couple of minutes on this, and this is rather subtle and quite a bit difficult actually, I must say, to decipher from the Kurkulu-Maldacena paper. But here is just a simple statement of facts. I'm not going to explain this, but the Kurkulu and Maldasena's idea or their proposal based on some elementary calculation is that this end of the world brane actually that starts out over here has an interaction with the boundary, and in the course of that interaction, as its mass increases, it starts bending until it bends to give this Poincare patch over here. Okay, so this is the picture in which the upper and lower are both in Lorentzian time, and here I have just included the Hartle-Hawking state, and this is the geometry. Again, you have this end of the world brane, which most important point, and the reason why all this will work out is because it sits behind the horizon over here. Okay? It sits behind the horizon. Now, I just make one comment actually, which might be somehow related to what Vijay was doing, that somehow there is a way in which you look at the two-sided black hole and introduce a certain projection operator made out of these BSL states. And then the thermophile double with that projection operator, most probably, I have not proved it, leads to some sort of a geometry like this, when this end of the world brane is very, very massive. So for the purpose of this talk, this is all I'm going to say about the end of the world brane, because it sits behind the horizon, and the geometry is qualitatively very similar to the geometry that we just discussed before over here. This one. Okay. By the way, if there are some questions, please stop me. I mean, I should have said this earlier, but are there any questions? Okay, if not, let me go ahead. So let's get back to the SYK model and try to compute this, or at least to present the answer for what this overlap is, which we already did. So this is the answer, which I mentioned before. And now the important point is that we have to evaluate this path integral over here along this curve. And this curve actually includes this imaginary sections also. So the fact that you have this type of state, which acts like a thermal state for a lots of operators, flip invariant operators, is coded into the fact that there is a classical solution over here, which you have to, so if you want to solve this problem semi-classically, you have to include the Euclidean classical solution over here that basically describes the black hole. Okay. And that's what you have to do. I'm not going to detail all this, but the Euclidean solution that you have to work with is precisely given over here. This is, of course, the famous map that takes you from the line to the circle. And if you use this solution to account for the state over here, then you can write down a path integral only along the real-time axis after you make a certain change of variables, which has been sort of discussed by a lot of people, Kamenev and collaborators, Verlinde and collaborators, and many others, and Julian and others. And you can arrive at a very simple path integral where this is a very simple canonical measure, and the action essentially is given by this potential problem. And we have this quench function. So now let me discuss the types of solutions over here. So if epsilon is equal to 0, for example, if this is 0, so this is the old SYK model because this term is not there. Okay, and then you essentially have the Liouville wall over here. Okay, If epsilon is also negative, that means minus of epsilon is positive, you again have a wall. There's no crossing. There's no crossing over here to this line. Okay. So the potential really never goes to zero at a finite distance. And this particular potential problem, therefore, essentially leads to a certain implication for the geometry. And the implication, you would have guessed, is the following: that because this motion over here, all motion in this potential is unbounded. So the particle just comes here, goes back all the way to phi equal to minus infinity at large times. And therefore, because of the unbounded motion, this is possible. And therefore, it is possible for f dot to go to zero. And this is the situation which we are familiar with, in which there's a horizon because the trajectory has f dot equal to zero here and f dot equal to zero here. Okay, so this is the normal case. All right. Now, what happens if epsilon is positive? If the quench parameter is positive, something very interesting happens, that the potential essentially dips down over here. So it dips down into the negative energy side. And now there are two types of solutions. There can be a bounded solution over here for particle oscillating, or there can be a particle which is sort of, sitting at the bottom of the potential over here. So the other possibility is that you have this unbounded motion. So unlike the previous case in which you only had unbounded motion, the presence of this parameter, quench parameter, appropriately chosen, can lead to the potential having a minimum like this. And the system can be just simply, for example, sitting at the bottom of this potential, okay, just not moving. That corresponds essentially to a certain state in which there is no horizon. Also, if the motion is bounded, phi is bounded, so f dot can never be zero. So these are the solutions or the motions of the dynamics that correspond to the absence of a horizon. So there is no horizon here because f dot never goes to zero along this trajectory. So this, I think, is an extremely beautiful point that was made by Kurkulu and Maldacena, that there is a certain way in which you pump negative energy, means you remove energy from the system, and you can get rid of the geometry with a horizon. So this is a very beautiful result, in my opinion. So the main lesson that we learn from here is, by tuning the quench parameter epsilon, we can pump out or pump in energy into the system and remove or form a horizon depending on whether the classical solution exhibits zero of the time derivative or no zero of the time derivative. It's a very simple, beautiful characterization of whether a horizon is formed or it is not there. Okay, so now clearly, I mean, if you understood this, then the next thing to ask is that what can we now do after Kurkulu and Maldacena have demonstrated that they have a geometry now without a horizon by giving a certain type of quench. So what you do is you take that geometry and you quench it again. You quench it again by pumping energy into the system and learn to solve the equations and see what happens. So this is exactly what we did. So here is a simple graph of the quench parameter epsilon of t as a function of time. So to begin with, epsilon, essentially, which I call epsilon 1 over here, is above a certain critical value. So you have to be above a certain critical value for the potential to dip and cross the x-axis. And this critical value in this problem is nothing but pi upon beta j. And since beta j is very large in the low energy limit, this is actually quite a small number. All numbers are small, and it's quite delicate actually how this all happens. Okay, so for a certain long time, you can continue to be in this state where the geometry does not have a horizon, and then suddenly you pump in energy into the system. So you essentially cross a certain critical barrier over here for the quench parameter and arrive at some value epsilon 2 that leads to unbounded motion again. So over here in this simple drawing, I have illustrated what I'm saying, that you basically start with a value of the quench parameter, which is this. So you get this curve over here, okay? All right. Then what you do, let the particle either sit here or do some periodic motion, and then at some time, capital T, give it a kick. You give it a kick and you raise it to another potential. You raise it means you pump in energy so that now the energy difference is this much. There's a certain critical amount of energy you can raise it to, which is very important for the possibility of having an unbounded motion. So if epsilon goes beyond this critical energy, critical value of the quench parameter, and hence the critical energy, then again you will land up over here and execute unbounded motion. So it's a very, very elementary, very simple point of how to do this. And all these equations actually can be exactly solved. I mean, these are just college algebra. And the nice thing is that in this simple model, you can actually do everything explicitly. Okay, and this is all given. The formulas are quite complicated actually. So you have to take a solution that is here, and that after the quench becomes a solution over here. So you have periodic functions over here, you have hyperbolic functions over here, as you would expect. Okay, now before I tell you something about the asymptotic solution to pull the temperature out, I'd like to tell you what's happening in space-time when we are doing this. So this picture is from our paper, where our notation was slightly different from this talk. Okay, so whenever T appears here, there is our F, the large diffeomorphism. So basically, the T of U is supposed to be understood as F of T. Okay, so the parameterization is slightly different. So what's happening here is that this is our Euclidean solution. This is the state we start with. Actually, this is a picture of the Hartle-Hawking construction, and we arrive at time t equal to 0, and the system then sort of propagates over here, and up till here, you just have an evolution in which you may think, if this evolution actually continued without the second quench, the solution will be like this, and there would be no horizon, right? But this second quench basically pumps energy into the system over here and changes this solution to precisely this one. And here explicitly you can calculate all these formulas, and it comes and hits over here with an F dot equal to 0. Moment F dot is equal to 0, information from this cannot reach the observer, and a certain horizon is formed asymptotically. You know, horizon is a subtle object, but only asymptotically you can infer. You cannot infer over here or here, but only asymptotically you can infer there is a horizon. So this is what is happening in the space-time picture. And now just want to tell you that I just want to show you the explicit solution actually. So if you solve this problem and you look at the formulas for F dot, which is exponential of phi, asymptotically, it essentially goes to e to the minus t times some constant. And the value of the constant is calculated from the solution to be this. You see, it is in terms of the first quench, which we started with, that is the given for the wave function to begin with. And then this is some parameter of the SYK model. And this is the exact formula for this constant over here. And from this asymptotic formula, you can read out the temperature of the newly formed horizon, black hole, whatever. And it is given by this formula. It is of this particular scaling form. And it's quite satisfying that you can actually see the formation, real time dependent formation of this black hole and calculate its temperature. So this is what we have done. Now you might wonder about why you get half. Maybe it's because we are working in large N limit, and perhaps there can be corrections to this type of mean field type of exponent over here. Okay, so now let me just in the few minutes I have just recall that our starting point was this overlap function, which in the low energy large N limit turns out to be this model that we worked with. And tuning the quench parameter epsilon of t, we can pump energy into the system to create a geometry with a horizon, a black hole with a temperature that can be calculated, and this is the result which I showed you. So this is just a simple summary of a project. The important point here is that the SYK model is a model with microstates. You know, it's a fundamental theory, and I think it's very important for us to solve these problems of black hole formation or Hawking radiation in terms of a microscopic theory. I fully appreciate a lot of work that is being going on, and so many beautiful talks in this conference in which the microstates are not discussed, and just the gravity is discussed, and very beautifully semi-classical gravity produces all these fantastic results of the page curve. It's very satisfying, but I would personally feel better if we can understand these things in terms of a theory which has explicit microstates of the black hole. Okay, so the next question, this is the question we are working on, and I'm not going to tell you anything much more except the obvious that is it possible for us to invent a model in which this quench parameter epsilon of t, which did our job so beautifully of getting rid of the horizon or getting in the horizon depending on its value, is it possible to have a model in which this is driven by dynamics? So that's the question we are looking at, and like everybody else, we have coupled the SYK model to a conformal field theory, which I'm not going to specify because it's a bit subtle, and the coupling is obvious. I mean, of the bath field, this is what replaces epsilon of t. Now, this is the dynamical field at the boundary of this bath, and this bath actually, you know, is some conformal field theory, garden variety. It's not important what the bath is, and it lives actually in this space. And this is the Lorentzian time, and we will of course need to construct the boundary states, the Euclidean time also. So this is the project we are looking at, and in fact I can tell you that this coupling essentially boils down to calculating the one-point function of the bath theory when you integrate out the bath degrees of freedom, and it turns out to be essentially a formula like this, where this is a Green's function. You have to compute with appropriate boundary conditions, and I have put sigma equal to 0 here and sigma prime equal to 0 here over here. Okay, so you get a complicated nonlinear integral differential equation for the particle f of t, which can be understood as some sort of a Coulomb gas, but I won't write down those equations now. But this work is in progress with Advait and Anurag. These are both students at Tata Institute, very outstanding students. And this is Gautam Mandal, he's a senior person, and myself. And this related work actually recently came out from Stanford by Chen, Chi, and Zhang, who have also coupled the SYK model to a bath. And they have not studied evaporation. They have not studied this problem, but they have studied this problem. Okay, so with those few words, thank you, and I'll be happy to take some questions.
Okay, thank you very much for your very interesting talk. Question, please.
Spenta?
Yes.
This is Vijay here.
Hi, Vijay.
Going back to your interesting comment, Is there some way, do you think, one might be able to make more explicit progress on deriving this semi-classical pictures that people have been talking about from the microscopics in the setting that you're talking about? I agree with you completely that much as it is satisfying to have the semi-classical picture, we would really like to have any example where we can calculate end to end.
That's right. So I think one fundamental problem here is the following. For example, if you look at the work of Ramsdonk and collaborators, very beautiful piece of work, but the boundary actually, boundary theory is assumed to be some conformal field theory with a sparse spectrum. And then you look at, the 4-point function and that technology, and you arrive at a very beautiful understanding of the page curve, etc. But the problem with the two-dimensional ADS2 or two-dimensional quantum gravity is that I do not know of any conformal field theory sitting at that point and evolving in time, which will produce this type of holographic dual. I mean, this is a very hard question actually, because many years ago, ourselves, I mean, and also Witten, ourselves means Gautam Mandal, Anirvan Sengupta, and myself, we discovered the black hole solution of dilaton gravity. And for many years, we tried to find some sort of a microscopic realization of this model of dilaton gravity. And to date, I don't know how to do it. So coming up with this Kitaev, Sachdev-Kitaev model, E-Kitaev model is an amazing progress, in which you have a theory which is not conformal, calculable, has Lyapunov exponents, and has a dual ADS2 geometry with a black hole. I think, yeah, so this is my comment to your, so sorry for being so long in the comment, but I don't see how it can be done very simply, unless you push this SYK calculations a little bit more.
Okay, thanks.
Yeah.
Sorry, question?
Yes.
So do you believe that studying the non-singlet sector of these old matrix models might help this question to answer it? Because SYK has disorder average. So.
Yes, I know, but disorder average doesn't bother me too much, because I can take some realization of the this J, I, J, K. You pick any actually, and this more or less this physics will not change. I think the disorder average helps us do analytic calculation, but I can do computer calculation with some realization of J, in which I'm not doing any Gaussian averages. So it's a technical thing, I think, but I think the Stanford people, especially Stanford and Steve Schenker and others, they seem to believe that somehow JT gravity is dual to a genuinely disordered system. I don't understand this very deeply, but there may be some truth in what you're saying. But coming back to the question that you asked about the non-singlet sector of the C=1 matrix model, there is work by, as you know, Kazakov, Kostov, and the other K, whose name I forget, and Kutasov. They did attempt to calculate the partition function with twisted boundary conditions, but I don't think that they were able to describe a black hole space-time. At least I don't see that. I don't see that really. Yeah.
Okay, thanks.